Yeah, thank you, everyone. So first of all, welcome everyone. And I'm going to present our research called Multimodal Cascaded Approach for Hierarchical Logo Tagging in Packaging Artwork Files. So I am Shishir, and this work has been co-authored by Anshul Verma, Yugal Gopal Sharma, and Dhanush Dharmaretnam. So we are from SGS&CO, an MNC from USA. So we'll talk about more about this work. So let me begin with. So let's talk about what are the key innovations that we are trying to project through this work. So one thing is that we have prepared a twin model based cascaded framework, which combines the detection capabilities of YOLO V8 to detect some logos. And then we are also using fine-tuned vision language models for automatic logo recognition. And then we are trying to generate some tags, particularly in nature, for these packaging artwork files. So the overall what we had achieved is that we have improved the artwork verification speed with 5 folds when compared to the manual verification. And we have also utilized some methodology for data annotation, which has reduced 30% time and cost in terms of manual annotation. And also we will see in upcoming slide that how careful fine tuning had led the VLM performance to improve to 24 folds when compared to its zero shot performance. So let's talk about the problem that we are trying to focus here. It's about the crisis that is being followed due to the manual logo verification. So in the current scenario, the challenges that we face is that in the packaging artwork files, any manual errors leads to a lot of recalls, which cost multi-million dollars to the company. Now, due to some inconsistent brand identity across products, which are which come across inconsistent logos on their products, it's a lot that happens. And also due to the regional standards of different compliance logos, it's very hard to keep track of all of these. And it's a very complex task here. And the next thing is that since the production artworks are very large in volume when they are processed every day, so manual processing and verification of each artwork is very tedious and takes a lot of time. Hence, it's more prone to errors. Now, why it matters? It actually matters due to three different, you can say, main pointers. One is the consumer trust, brand integrity, and the legal compliance in terms of business. So when we talk about consumer trust, so any errors in the regulatory symbols can actually lead to a lot of significant penalties on the brand and the provider itself. And due to these, if there are inconsistent logos across the products of a brand, it might damage its reputation as well. Plus, if we fail to follow all the regional variations of all the compliance which is required to be present, it might have a lot of costly legal implications to the brand itself. So there has been a lot of work which was done previously on logo detection and tracking, but the critical gap was that all the existing solutions, they only focus on the brand logos, but they ignore most of the regulatory symbols, sustainability indicators, and all the compliance related essential marks, which are present usually in the packaging artwork files. So as you can see in this current slide, here are some examples of the production artworks, which are used to create the artwork which are present on the boxes that we see every day in the shipped containers or the items that we receive. So as you can see, they contains a lot of elements in it like graphics, text, and logos and all those things. So identifying the exact logo and trying to tag them on these packaging artworks is a challenging task given the current available frameworks. Here you can see there are some examples of the logos. As you can see, there are some compliance logos, some identification of particular brands, and we have sustainability logos and some nutrition elements there as well. So let's talk about the cascaded solution that we have proposed. So it's a two-step solution where we use two different kinds of models to perform the task. In the first step, we use a fine-tuned object detection model, YOLO V8 in this particular case. And in the second step, we use a fine-tuned vision language model. And here we used Florence 2. We'll talk about all the rationales behind why we have chosen this approach. So what happens? Let me go through the approach, how it works. So first we input an artwork image, which is given to the fine-tuned object detection model to detect the logos present in the artwork. And then the detected logos are provided their primary classes. Once these logos are detected, they are extracted and sent to the vision language model as an input, which generates appropriate tags in a proper hierarchy for those specific logos. So when we talk about hierarchy, it will be like the primary class, the secondary classes, and some description about that particular logo. So it has some key features like we are using the stage 1 as a YOLO V8 and the stage 2 we are using Florence 2. We can see some significant performance metrics here, which we will try to compare with our experiment that we have done. So overall, we have tried to target 7 primary logo categories in this particular work. They are namely branding, sustainability, health and safety, material identification, eco certification, social media, and compliance. And every other category which hasn't been classified into any of these, we call them as others. Moving forward, so the heart of every model or approach that has been fine-tuned is the data set on which it has been trained. So let's talk about our data set. So before moving forward, I would like to mention that we have applied a human in the loop approach to prepare this data set, which we can discuss further in the upcoming slides. So for this particular step, since it's a two-step approach, we have 2 different data sets to train 2 different models. For the logo detection, we have the logo detection data set comprising of 432 annotated images. And for the tagging, we have 1,114 tagged logos. Now it is an iterative annotation for both YOLO and the tagging data set. So the detection data set, why it's peculiar here? Because it's also suitable for the small logo detection, and it contains variations of logos beyond the typical brand that is in the current data sets, which are present in open source. And for the tagging, we have applied a VLM assisted annotation, for which we utilize Llama 3.2. After the tags generated by this open source model, we have utilized human validation and correction to prepare the final hierarchical tag structure as a dataset. So the key differentiator of this dataset from already available ones, like the popular ones, LogoDet 3K or Open Logo datasets, is that we captured all the spectrum of logos which are present in the packaging artworks, from compliance, sustainability, and safety symbols to brand logos as well, which is not restricted just to the brand logos. So moving ahead, here we have the human in the loop approach that we have been discussing so far. So we applied this approach in both the data sets. So let's look into logo detection dataset, how we have prepared this. So first we have on our hand a lot of artwork images, which we called as a raw dataset here. So we randomly sampled and prepared some manual annotation of a fraction of these images and put them into a database called annotated images. After that, we trained the preliminary YOLO V8 model for logo detection. So once this training was done, we have again random sampled without replacement from the artwork dataset and got some unannotated images on which we ran the inference on the preliminary model. So once we got the inference, we validated the output and corrected any inaccuracies in the detected output. Once we corrected all the outputs with a human, then it was again fed back to the annotated images dataset. And this was done in multiple iterations. So this dataset kept growing. And finally, we had the logo detection dataset. So you see, we have used a machine learning assisted approach to annotate this dataset. Similarly, in the logo tagging dataset, we had a bunch of logo images in our database. And then we utilized the Llama 3.2 11 billion vision instruct model, equipping with a prompt to generate the hierarchical tags, which created us the comma separated tags. After this, we got these tags. We validated all these outputs through human in the loop system. And then once this output is validated, we have again transferred it to the tagging dataset. So this way, we have prepared both of these datasets. So these are the prompts which we have used for both annotation and inference. So the prompt on the left, you can see, this is the one that we have used to get annotations from Llama 3.2 and all other large language models which we have utilized in our experiments, which we will be showing in the upcoming slides. As far as the vision language model for our step 2 approach, the Florence 2 is considered, we have only utilized a particular task prompt called detailed caption, which is a predefined task prompt. And it is a limitation of the Florence 2 where it accepts only a specified set of task prompts only. So we were bound to use this. Now, as you can see in the original prompt of the large language models, we can define a lot of fields which we want to identify. We have given the definition of all of them and provide the output structure, which gives us the tags in a comma separated list of tags. Now, moving forward, this is the data set distribution of our logo detection data set. So as you can see in this particular bar chart, there is a huge class imbalance among all the different kinds of logos present in the artwork. As you can see, the branding and the health and safety, along with the others classes, has the highest abundance, while other peculiar classes, for example, compliance, sustainability, material IDs, eco-friendly certifications, and social media, they have lesser amount of representation, which is actually the distribution in the real world as well. So these elements are less in number in artworks, and they are flooded with the brandings and health and safety symbols. Now, to deal with this class imbalance, we have utilized some advanced data augmentation techniques such as cut mix, mix up, and mosaic. These are the classic ones. And we have also utilized some cropping, warping, rotations, and other color and flip related features so that we can capture the variances from different angles and scene instances. We've also applied weighted training in which we utilize the weighted Adam optimizer, which applies the class weights to compensate for the class imbalance present in the dataset. So moving forward, here are some of the experimental results that we have for comparison in the step one, mostly with the detection performance. So we actually trained three different models, the Euro V8 and the faster RCNN and detection transformers for this tasks. As we can see in this table, the mean average precision across all the classes in the intersection over union threshold of 0.5, Euro V8 performed the best, although for the threshold of 0.5 to 0.95, the faster RCNN was the best. But still, we chose the YOLO V8 for a particular reason. As you can see, the number of parameters involved in the YOLO V8 model is about 1/4 of all the parameters in the other models. So due to the balance of speed and accuracy, we chose the YOLO V8, plus it has 4 times lesser parameters than its alternative, which makes it very suitable for deployment on our 2 gigabit CPU container in real time for production. And other thing which distinguishes it from other models, it is ability to process the data in the real time. Now moving ahead, for the tagging performance, our star was Florence 2 model. So as you can see, the zero shot performance of the Florence 2 was 0.03, which partially can be blamed on the amount of or type of prompts it can handle. But after the fine tuning, you can see the ROG LF1 score, which is a metric to identify the generation quality, how accurate is it to the original one, is significantly improved. If we want to quantify it, it's about 24%, 24 times improvement in the performance. So when we compare it to other models which we have tried experimenting, we have experimented with GPT-4o, Llama 3.2 in zero shot as well. Also the adapted versions of Llama and Florence 2. So as you can see in the zero shot, the GPT-4o performed the best, although it was not quite good enough as a proper model to be used in production. We can see that the Florence 2 was able to be performing as much as similar as Llama 3.211b when fine-tuned. So the key finding was that even with the lesser number of points on which it was trained and the smaller model, the Florence 2 model actually matches the larger Llama 3.2 performance with 10 times lesser parameters than the other. In this graph, you can see that we have trained both the models on LoRa, the low rank adaptation, and also we tried to quantize them. So the blue ones you can see are the Florence models, and the magenta one are the Llama models. So in the Florence one, you can see that when it was fine-tuned with the different rank and scaling factors, the performance shot up abruptly from zero shot to the better ones. And we can see it's quite increasing linearly. And finally, we have the depicted score as earlier. On the other hand, on the Llama models, it definitely improved the zero shot, but it didn't improve much after improving the rank and scaling factor. And when quantized, it actually decreased the performance of the bigger Llama model. So you can see that the difference in the number of available parameters is very less in Florence 2 when compared to the Llama model, making it suitable for production use case. So after fine tuning, we have these two best configurations of the open source models, namely the Florence 2 and Llama. So both of them worked best when the rank and scaling factor was 64 and 128 respectively. And the training cost of Florence 2 was about 1/3 of what was for the Llama. Plus the training time was also less than half of the Llama models. But we can see the performance, which is measured by the ROG LF1 scores, are almost similar for both these models. Although the inference cost is exactly the same for these models, but the memory usage of the Florence 2 is significantly lesser than the Llama models. So the Llama models used 3 times more memory than the Florence 2, making the Florence 2 as the right candidate for production use case. Now, if we want to assess the performance of these models for per logo type in real world, we can see this spider charts showing us the performances. So as you can see, we have tested with some state-of-the-art models like GPT-4o, Llama 3.2, HiQ, Sonnet, and also the adapted versions of Llama and Florence. So we can see all the open source zero shot models were not very well equipped with understanding of all these tag generations. And even the open zero shot Llama also struggled to maintain good performance across all logo classes. But when they are adapted, they are fine-tuned. You can see they have significantly improved their performance across all the primary classes, even though the compliance struggled a little bit because of large variation in the types of compliance logos. So what we actually solved here is like now the models were able to distinguish between different material types present within the recycling symbols. And also they were trying to, they were able to differentiate between the different sustainability logos like eco-friendly, cruelty-free, and different vegan variations as well. And the region-specific compliance symbols were also being able to be identified. So the key finding was that adding an adaptation block to both the models, even Llama and Florence 2, they improved the performance of these VLMs across all the primary logo classes. The success of this system can be attributed with the fact that even though the subtle variations in the logos were present, which are typically cause of the manual verification errors, they were being greatly handled by the system here. Now let's talk about the business impact and the return of investments of these systems. So as we have already discussed that the artwork verification speed has been improved by 5 folds and the annotation cost of the dataset preparation reduced by 30%. We can also see that using the lesser parameter models reduce the training time by 20% as well. So the key benefits that we were able to achieve were the compliance tracking, which can be automatically done through by identifying different regulatory symbols, which actually reduces legal risk across different regions, and the brand consistency. The system allows to ensure that all the products of the same brand have a uniform brand representation across all kinds of packagings. And one more thing is that these production artworks are handled in a very large volume. Hence, like processing all of them manually was very hard. But when we try to scale these models, using the smaller models was as a good cost because it doesn't increase the proportional cost very much. Now the error reduction, definitely it's an improvement because since like the manual verification does definitely takes a lot of time and leads to costly recalls of the artworks. Using this system as an assistant can help us reduce those errors a lot. Now here, I have tried to demonstrate a small example of how the system looks like in actual work. So as you can see, we have an input artwork here with all the diagrams and everything. It is fed to the logo detection model, which detected all these logos in bounding boxes. And then the tagging model tries to generate these comma separated tags in hierarchy. So if you can observe that the first tag is always the primary class of that logo, and the remaining tags show them secondary classes or the description about what the logo is about. And the total processing time of these artworks is on an average about 6 seconds per artwork for a complete analysis. Now let's talk about the limitations and future directions where we can go ahead with this research. So in the current, a major limitation is that we have only fixed for the 7 logo categories yet. And there might be a lot of rare types of logos which might not be captured by this current dataset due to its size. And also sometimes due to occlusions and distortions, the performance does degrade. So more training data and augmentation might help it. Now there is a potential case of overfitting with the smaller fine-tuning data sets, as if there is some different variation of particular logos which are not present in the data set, it might be overlooked by the models. So looking at these limitations, the future work can be expected to be addressing the dataset expansion to incorporate more logo variations that can address industry-specific symbols, and also to integrate the human feedback reinforcement learning for continuous improvement. And currently, as you can see, the tag generation is mostly in the English language for all the symbols, which can be further extended to multilingual support in future. And also the real-time adaptation can help in online learning through the verification feedback from operators, which can actually help the model learn in real time. So let's jump into the conclusion here. So the key contributions that our work provides is that we have provided the first cascaded framework, which specifically targets the packaging artwork logos. And also we have a novel data set which captures the regulatory and compliance symbols And our cost-effective fine-tuning methodology achieved 24-fold performance improvement, and hence we have a production-ready system which has a proven business impact. So this work actually demonstrates that even if you're using smaller models and if you carefully train them and efficiently train them enough, they can match or even exceed the performance of the larger models. Hence, it can reduce the lot of computational costs, which will be very ideal for advancing this AI to be more accessible for production use case in the industry. So with these few things, I would like to rest my presentation here. And thank you everyone for your time here. Now we are open to questions.